Welcome back. In this section, we'll be looking at the graphs of the other four trig functions, and we'll also be looking at properties of those four trig functions. What we won't be doing is transforming them ourselves, graphing a transformed secant graph or transforming a graph of cosecant. That's not on the agenda for today, but we will need to know what the basic graphs look like, and that will help us figure things out about properties of our secant function or cosecant function or whatever other function we're looking at. The way that we'll do this is by thinking about all of those functions in terms of sines and cosines, because all four of them, tangent, cotangent, secant, cosecant, all could be written in terms of sines and cosines. So if you know the properties of sines and cosines, then you know the properties of the other four functions. So as an example, I know that secant is the reciprocal of cosine. And so wherever cosine is equal to 0, secant would be undefined because it would be 1 divided by 0. And that means that secant is going to have a vertical asymptote whenever cosine is equal to 0. So in other words, if you know the x-intercepts for cosine, then you know the vertical asymptotes for secant. You could also say some other things like, since secant is 1 divided by cosine, this fraction could never be equal to 0, and that's because a fraction is only ever equal to 0 when the top is 0, and here the top is always 1, so that means this fraction will never be equal to 0. Secant could never be equal to 0, which means secant has no x-intercepts. Secant and cosine, they're both positive at the same time and both negative at the same time. So if cosine is negative, then so is secant. If cosine is positive, then so is secant. And those are the sorts of things that we can come up with. If we're thinking about how secant is just the reciprocal of cosine, then we can say all sorts of things about locations of intercepts and locations of asymptotes, rather, and all the rest. And I could do a similar sort of thing about cosecant and sine, since cosecant and sine are reciprocals. Wherever sine has its x-intercepts, cosecant would be undefined. It would have vertical asymptotes. So now let's have a little bit of a look at the graph of these functions, and you'll notice that I've drawn actually a couple of graphs on the same axes. Here I've got the graph of secant in red, and underneath it in a little dashed gray, I've got my graph of cosine, and you can see that whenever cosine is 1, so is secant. Whenever cosine is negative 1, so is secant. We also have all of those places where cosine has its x-intercepts. Those are the places where secant has its vertical asymptotes. So again, if you know stuff about about cosine, then you automatically also know things about secant. And I've done a similar sort of thing with the graph of cosecant, where I've drawn underneath it the graph of sine, and we can see again, wherever sine is 1, so is cosecant. Wherever sine is negative 1, so is cosecant. And whenever sine had its x-intercepts, cosecant has its vertical asymptotes. And so from this, we get a bunch of properties for the secant and cosecant function. The domain is basically all of those things except for the asymptotes. So excluding all the asymptotes for secant, excluding all the asymptotes for cosecant, the domain is everything else. The range for these ones, you might have noticed on the graph that for secant and cosecant, they're always either 1 and larger or negative 1 and smaller, that there's no secant that's between negative 1 and 1. And same thing for cosecant. There is no cosecant graph that has values between negative 1 and 1. The y values are either 1 and larger or negative 1 and smaller. So for both of those graphs, the range is everything up to and including negative 1 and everything from 1 and onwards. And as far as the vertical asymptotes go, again, this is the same list of the x-intercepts that we would have had for cosine. It has x-intercepts at pi over 2, minus pi over 2, 3 pi over 2, minus 3 pi over 2. So secant has those locations for its vertical asymptotes. And sine has x-intercepts at 0 and pi and 2 pi and 3 pi. So cosecant has its vertical asymptotes there as well. For tangent and cotangent, I'm just going to sort of keep in mind that tangent and cotangent are both definable in terms of sines and cosines. Tangent is sine divided by cosine, and cotangent is cosine divided by sine. So if we know stuff about sines and cosines, then we know stuff about tangents. Again, wherever the denominator is 0, that's where you'll have vertical asymptotes. So whenever cosine is 0, in other words, whenever cosine has an x-intercept, tangent will have a vertical asymptote. Whenever sine is equal to 0, the whole fraction will be equal to 0. In other words, whenever sine of x has an x-intercept, so does tangent. So if you know the x-intercepts for sine, then you automatically also know the x-intercepts for tangent. And if you know the x-intercepts for cosine, then you know the vertical asymptotes for tangent. And of course for cotangent, it would be the reverse. Cotangent is cosine divided by sine. So again, wherever the bottom is 0, that's where cotangent would have its vertical asymptotes. Whenever the top is 0, that's where cotangent would have its x-intercepts. And here I've got the graph of tangent given to us. I've drawn it here where I've got x-intercepts at 0 and at pi, and there would also be another one at 2 pi, then 3 pi, and so on. Whenever sine has an x-intercept, so does tangent. And all the vertical asymptotes at negative pi over 2 and pi over 2 and 3 pi over 2, those are all the places where cosine has its x-intercepts. And I could do similar sort of thing for cotangent. Wherever it's having its x-intercepts, that's where cosine has its x-intercepts at pi over 2 and 3 pi over 2, and so on. And all those places where we've got vertical asymptotes, 0, pi, 2 pi, and so on, those are places where sine has its x-intercepts. Something else, hopefully, that you've noticed now that we've seen all 6 graphs is that there are 6 different graphs in total, but there's really kind of like 3 pairs. Sine and cosine both look like each other. They're both oscillating up and down. We have cotangent and tangent both kind of look like each other, and secant and cosecant also kind of look like each other. The cosecant graph and secant graph both kind of look similar. One is sort of a shifted version of the other. And if we're looking at tangent and cotangent, they're almost like reflected and shifted versions of each other. So that's a nice thing to keep in mind, that if you know the shape of one graph, you also know the shape of its cofunction. So sine and cosine, similar shapes. Secant, cosecant, similar shapes. Tangent, cotangent, similar shapes. And then for all of our properties, for these, we've got for tangent and cotangent x-intercepts. They definitely have them. Tangent has the same x-intercepts as sine. Cotangent has the same x-intercepts as cosine. And then for the asymptotes, whenever cosine has an x-intercept, tangent has a vertical asymptote. Whenever sine has an x-intercept, cotangent has a vertical asymptote. The one thing that was different about tangent and cotangent as opposed to the other four functions, sine, cosine, secant, cosecant, they all had a period of 2 pi. Tangent is the one exception in that it's got a period of pi. Okay, so now I'm going to use what I know about my sine and my cosine function to figure things out. I want to know 6 different x-intercepts for this function. 2 tangent negative 1 over 4x. And so the one thing that I know is that if I'm thinking about y equals 2 tangent of negative 1/4 x, that tangent is the same thing as sine of negative 1/4 x divided by cosine of negative 1/4 x. And if I'm thinking about finding x-intercepts for this function, I know that tangent is going to have an x-intercept whenever the numerator is equal to 0. So in other words, I need to find my x-intercepts for sine of 1/4 x. Once I know those x-intercepts, those are going to be the same as the x-intercepts for our tangent function. because wherever the top of our function is equal to 0, that's where the fraction itself is equal to 0. So if you wanted to know where is 2 times tangent of negative a quarter of x, where is it equal to 0, that would be the same as asking where is sine of negative a quarter x equal to 0. And to figure that out, that's not hard to do, because if we're thinking about building up our answer for this, I would start off with saying for y equals sine of x, we know that the x-intercepts are at 0 and at pi and at 2 pi and 3 pi and 4 pi and so on. So all of those whole number pi's. So there we go. I've got 1, 2, 3, 4, 5, 6 of them. Good, good. And if I wanted to think about y equals sine of negative a quarter x, that would be the sine graph where I've taken all of the x values and divided them by negative 1/4, which is the same as taking all of my x values and multiplying them all by negative 4. So if I wanted to have my x-intercepts for sine of negative a quarter x, I just need to take my original x-intercepts and multiply them all by negative 4. So 0 minus 4 pi minus 8 pi minus 12 pi minus 16 pi and minus 20 pi. Those are all of those are places where I've got x-intercepts for sine of negative a quarter x, and I had said at the beginning that wherever sine of negative a quarter x has its x-intercepts, so will tangent. So now if I wanted to give my answer here for the negative 2 tangent of a quarter x, so for 2 tangent of negative a quarter x, I can say that we have x-intercepts are 0, 0, negative 4, 0, negative 8, 0, negative 12, 0, negative 16, 0, and I forgot all the pi's. Oh, I'll try that again. 0, 0, negative 4 pi, 0. Try that. Negative 8 pi, 0. Negative 12 pi, 0. Negative 16 pi, 0. And negative 20 pi, 0. And those are 6 that I chose. I mean, I could have gone for a different start of 6 intercepts for sine. So I could have chosen 0 pi, negative pi, 2 pi, negative 2 pi, 3 pi, and that would give me a different set of 6 x-intercepts. Remember, there's infinitely many x-intercepts for both of these graphs. I just needed 6 of them. Any 6 will do. So there we go. Those are the 6 that I've come up with. At 0, minus 4 pi, minus 8 pi, minus 12, minus 16, and minus 20 pi. Okay, so next part, we wanted to look for 4 different vertical asymptotes for this function, 3 cosecant of 2x. And I'm going to think about what I know, which is that cosecant is the reciprocal of sine, so 3 cosecant of 2x is the same thing as 3 over sine of 2x. And so if we were wondering where are the vertical asymptotes for cosecant, then you would be asking yourself, where is the denominator of this fraction 0? Or in other words, if we're thinking about x-intercepts for the function y equals sine of 2x, those are going to be the places where we have vertical asymptotes for our 3 cosecant of 2x. So I'm going to do the same thing that I did in the previous question. I'm going to start with the basic shape, in this case sine, think about where its x-intercepts are, then figure out where are the x-intercepts for sine of 2x, and once I know that, then I'll know where the vertical asymptotes are for cosecant. So for sine of x, if we're thinking about x-intercepts, and I only need 4 of them for this one, I could say I have them at 0 and at pi and at 2 pi and at 3 pi. There we go. And so if we were asking the same thing now about sine of 2x and asking where are the x-intercepts, sine of 2x, I'm taking all of the x values and dividing them all by 2. So if we wanted to know where are all of my x-intercepts, I'll take the ones that I had and divide them all by 2. 0 divided by 2, pi divided by 2, 2 pi divided by 2, that's pi. 3 pi divided by 2, that's 3 pi over 2. And now I found the locations for x-intercepts for sine, and those are going to be also the locations for vertical asymptotes for cosecant. So now I can answer my question, which is for y equals 3 cosecant of 2x. I can say that the vertical asymptotes are at x equals 0, x equals pi over 2, x equals pi, x equals 3 pi over 2. And I only needed to come up with 4 of them, so there's 4 equations for vertical asymptotes. But once I've done a few of them, I can also see a pattern, and it looks like I'm having them every pi over 2. So there should be one at 2 pi, and at 5 pi over 2, and 3 pi, and negative pi over 2, and negative pi, and negative 3 pi over 2. So in fact, I could generate as many vertical asymptotes for cosecant as I want.